Hello. Yeah, welcome to another edition of the COVID-19 show. All right, this one is going to be a little more theoretical about the whole set 12 idea of non-homogeneous linear ODEs. So the title of this is Why is Y equal YH plus YP? And I can change that to y is YH plus YP, the general solution to Ly equal G of t. Okay, and remember that YH is the general solution to Ly equals 0, so the associated homogeneous equation, and YP is one solution, a particular solution to Ly is G of t. All right, so to be the general solution, we need two things. We need a family of functions, it will have constants in it, such that every function in that family, every choice of constants gives you a solution, that's one. But two is that every solution to the ODE is contained in that family, right? So, step one, all right, if I take L of YH plus YP, okay, because L is a linear operator, this is L of YH plus L of YP, all right, but we already know that L of YH is 0 and L of YP is G of t, right? So that means that this sum is a solution to the ODE, right? Now, for 2, we want that every solution is found in there, right? We might have infinite number of solutions in this family, but it's missing one. In fact, that happens sometimes with nonlinear things. We got every solution but y equals 0 because we had a 1 over the constant was in there. Well, anyway, never mind about that. So let's suppose that we have two solutions to the non-homogeneous ODE, right? They're calling them Y1 and Y2. This is a lot like that first video I did that was sideways. Was that number, I think it's number 10, but it's problem 10. All right, but we got two solutions here. All right, actually I'm wrong about the sideways one. This is like yesterday's. So what happens if we take the difference of these? If we take L of Y1 minus Y2, this is L of Y1 minus L of Y2. Why? Because L is a linear operator. And this is G of t, and this is G of t. I get G of t minus G of t, I get 0. In other words, the difference between any two solutions is a solution to the homogeneous equation Ly equals 0, right? So that means I can get from any one to any other by adding a solution to Ly equals 0. So that way I can get the general solution by starting with any old YP, and then I can get to any other one by adding an element of YH. Hope that makes sense. All right. So I want to talk a little bit about how this relates to something a lot more concrete than we can actually get our hands on. This space of functions is really a vector space, but it's a little bit hard to imagine because it's infinite dimensional. Wow. And that's pretty cool to think about infinite dimensions. But let's think about 3 dimensions. We live in 3 dimensions. All right. So there's an analogous statement to this YH plus YP that has to do with solutions of linear equations. Okay? So the set of all solutions to AX is B, where X is a vector, A is a matrix, and B is a vector, is X is XH plus XP, where XH is the general solution to AX equals 0. That's the homogeneous solution. and xp is one particular solution to ax equals b, the original one. I can actually do the same thing we had before. I can actually kind of prove this. If I take a of x h plus xp, those are vectors. This is vector multiplication. We know that's axh plus axp. All right, so that's equal to 0 plus b. So I got that first thing. All right, for any vector in xh, this works. All right, and then number 2, that was 1. And number 2 is that a times the difference of two vectors, and these are two vectors that solve the original guy. That's going to be ax1 minus ax2, so that's b minus b equals 0. Okay, so again, the difference between any two solutions to ax equals b is a solution to ax equals 0. All right. So, I want to illustrate this with a solution in 3 dimensions where you can actually draw everything. All right, here's a system of 3 equations and 3 unknowns. And the vector x can be written as x, y, z without the vectors. Okay, so let's solve this. Let's solve this in the way we've done before. We make the augmented matrix 2, negative 2, 1, 1, negative 1, 2, 0, 0, 3. We add the column 1, 2, 3. And we want to find the reduced row echelon form of that. All right, let's see. First thing I want to do is multiply this bottom row by a third, and I get 0, 0, 1, 1. Okay, let's also take that one minus twice that one, be the first row. That one minus twice that one is 0. That one, 0. That one, let me see, I think I'm screwed up. Yeah, that one minus twice that. That one minus twice that is 0. That one minus twice that is 1 minus 4, that's negative 3. That one minus that one is 1 minus 4, that's negative 3. And in here I get 1, negative 1, 2, 2. Okay. Oh. That is just negative 3 times that. So this could be 0, 0, 0, 0. Taking that plus thrice that. Then I get 1, negative 1, 2, 2. Leave that alone. And I leave this alone. All right. So let's see. First, let's move that one on top and that one on the second one. I can permute the rows. Okay, and now I can take this row minus twice that row and get 1, negative 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay, all right. So this means that x minus y plus 0z is 0, and 0 times x plus 0 plus y plus z, that should be a 1, plus z is 1. And then I get 0 equals 0 on the bottom, okay? And you might remember, sometimes if you start with 3 equations and 3 unknowns, you end up at the bottom with getting something like 0 equals 1. And that way, that's false, so that means there's no solutions to the initial system. But here, we're cool, we get 0 equals 0. It also means that these 3 equations and 2 unknowns are really equivalent to those 2 equations and 2 unknowns. Okay, and let me draw a picture to that. Right? So what we get is basically that x is y and z equals 1. So in 3 dimensions, here's x, here's y, and here is z. The solution is on the plane z equals 1, and I can draw a picture of that plane, like that. Okay. And the solution is actually x equals y in that plane. Here's x equals y is this little line here. So this little line in three-dimensional space is the solution. I can write this solution in this way. X is equal to I, a constant, times 1, 1, 0, plus 0, 0, 1. Right? This is, right, for this, in this part here is going to be the xh vector. In this here is the xp vector. I found one solution to the system, 0, 0, 1. If I have 0, 0, 1, I multiply this, I get 1, 2, 3, just that works. And then this 1, 1, 0 is the general solution to this matrix times x equals 0. Okay? So this is a lot like a solution to a first order linear ODE that's non-homogeneous. I've got a non-homogeneous solution to the original equation, just one of them, plus this solution to the homogeneous equation. All right. And again, I can choose any old particular solution. Let's just do another one. If I take x I'll call it a now, a different constant, times 1, 1, 0, plus 1, 1, 1. Here's a different xp. There's a solution that's actually right there. The solution 1, 1, 1 solves this guy. I don't do the multiplication, but I can start at 1, 1, 1, and then add any constant multiple of 1, 1, 0, and I get exactly the same line, right? All right. So, yeah, so I hope this gives you a little bit better feeling for y equals yh plus yp, because you also get the general solution x is xh plus xp in this nice three-dimensional system where you can kind of visualize things a little bit better. Okay, stay healthy, and I really hope you're doing okay. I'm doing fine. We got plenty of toilet paper, and we got plenty of food. All right, so thank you. Goodbye.